In this lecture, we're going to talk about development length of reinforcement. Development length refers to the fact that in order for a rebar that is embedded in concrete to develop its full yield stress, it needs to be properly anchored inside the concrete. There are basically two ways to do that. The first one is through a straight embedment, and we can see here a case of a pull-out test in which a bar shown here inside a piece of concrete here, right? It's being pulled with a force T, and in order for that bar not to come out or to pull out, it needs to transfer that force T into the concrete via shear stress, right? And so we're going to have here some shear stress in the concrete resisting this tensile force. So you can see here on the right, the bar stress starts to decrease as you move along the length of the bar, while the bond stress or shear stress going into the concrete increases and then drops off. Beyond this point here, the bar has been fully developed and no more stress is going into the concrete. And so basically what we have is a transfer between bar stress and bond stress. So then the question is, how long does this bar need to be inside the concrete in order to fully transfer the complete yield stress that could be put in the bar? So basically, can we yield the bar without it coming out or breaking the concrete? So the mechanisms by which that happens are basically two, right? There is this anchoring force that comes from the fact that the rebar has these deformations along the way, and these deformations cause a certain bond contact to happen, as shown in here. And then there is also friction along the length of the bar, and because this force is inclined, there is also a radial component, as shown right here, that creates potential splitting in the concrete. This can be seen here in figure 5.8 of your textbook, typical splitting failure surfaces. So when you're pulling on this bar, there are radial forces that could create splitting. And so if you're trying to develop a number of rebar, like let's say here we have two rebar, they have to be spaced out far away enough such that these fields of stress don't begin to interact with each other and creating sort of a plane of weakness, as is shown right here. The basic formula that ACI presents in order to compute the development length is shown right here. And that formula depends on several factors, and this has been studied for many years, since the late 1970s. So LD is the development length, and this is measured in inches. That clearly depends on the diameter of the rebar, right? That's shown right here. It also depends on the type of rebar, whether the bar is epoxy coated or not, the size of the rebar, the location of the rebar with respect to the beam or the structural member, and also in relation to the other bars. The type of concrete plays a role as well. So if we're talking about lightweight concrete, there is a factor included there to account for this. Obviously, it depends on the yield stress of the steel and the compressive strength of the concrete. It also depends on the location of the bar. Here, this factor CB depends on the smallest distance measured from the surface of the concrete to the center of the rebar being developed, and the center-to-center spacing from one rebar to the other, right? So it depends on how far the rebar is placed in relation to the surface of the concrete and in relation to other rebar. This formula sometimes is a little complicated to apply, so there is a nice table here that summarizes these results for rebar number 6 and smaller and number 7 and larger. So these formulas are shown here for different types of rebar, and also depending on two cases. Case number 1, whether the clear spacing of bars being developed is not less than dB, and stirrups are also used based on the minimum code requirements. And so you can have, this is case 1, this is an illustration of how that works. So basically, in order for you to be in case 1, you need to have stirrups satisfying the minimum requirements from the code. The spacing between rebar has to be greater than the bar diameter, and the surface distance also has to be larger than the bar diameter. If you don't meet these requirements, then you fall into case 2, which is a case in which the spacing between rebar is more than 2 times the bar diameter, and the clear spacing to the surface is more than the bar diameter. So this would be case 2, and the formulas are slightly different from one case to another. And if you don't meet these requirements, then you fall, as I said, into a different category where the formulas are a little bit more penalizing. So either you have stirrups and the bars can be placed closer together, or you don't have stirrups and the bars have to be placed farther apart. If you meet these requirements, you can use the formulas shown right here. If you don't meet those requirements, then there is a penalty and the development length is larger, and then you fall into this category right here. We also have compression development length, which are clearly smaller than the tension development length, and this is because some of the force is transferred by bearing at the end of the bar, and because there are no cracks in such anchorage region, right? The member is completely in compression, and so the integrity of the concrete is better. The other way to anchor rebar is by using a hook at the end of the bar, and this significantly reduces the lead-in length or the requirement straight development length, because you're being helped by this bearing stress happening at the hook, and also because of the stress that develops here in this part of the bar. Right, so one way to do it is through a 90-degree hook shown right here, or by a 180-degree hook as shown here. There are some requirements for these hooks, like for example, if you use a 90-degree angle, you need to have 12 times the bar diameter extension on the straight part, or if you use a 180, then you need to use 4 times the bar diameter in development length. In both cases, the straight development length is the same, LDH, and that is given by this expression right here. and that expression can be reduced by a certain factor depending on the location of the bar, the type of hook, the diameter, the cover, and so you're allowed to further reduce that length if